Introduction. So what is titration? Titration is a common analytic technique in chemistry used to determine the unknown concentration of a solution by reaching it with another solution of known concentration, called the titrate. The process is carried out by the gradually editing the titrate from a burette into an analytic the unknown solution until the reaction reached at the equivalent point, the point at which the amount of titrate added is chemically equivalent of the amount of substance in the sample. An indicator is often used to signal the end of reaction, usually by a distance color change. For example, in acid-base titration, methyl orange is common indicator that change from red in acidic solution into a yellow in a basic solution. Titration is widely used in laboratories, industry, education, and environmental science. It plays a key role in quality control, water testing, pharmaceutical analysis, and many other fields where the precise chemical measures are essential.
Titration is the slow addition of one solution of a known concentration called a titrate to a known volume of another solution of unknown concentration until the reaction reaches neutralization, which is often indicated by a color change. The solution called a titrate must satisfy the necessary requirements to be a primary or secondary standard. In a broad sense, titration is a technique to determine the concentration of an unknown solution. There are 4 types of titrations: titration of strong acid and strong base, titration of strong acid with weak base, titration of weak acid with strong base, and the last one is titration of weak acid and weak base. Next is some of the common types of indicator. First one is phenolphthalein, which is suitable for strong acid, strong base, and weak acid, strong base. Next is methyl orange, which is suitable for strong acid and weak base. And the last one is bromothymol blue, which is suitable for strong acid, strong base.
Next, we go to the methodology. The methodology of titration involves several well-defined steps to ensure accurate and reliable result. First, a clean burette is filled with the titrate, a solution of known concentration such as sodium hydroxide is an acid-based titration. The burette allows for precise measurement of the volume delivered. Next, a measured volume of the solution with unknown concentration is transferred into a clean conical flask using a pipette. The pipette ensures a consistent volume is used each time, usually 25 ml. Before starting the titration, a few drops of a suitable indicator are added to the analyte in the flask. The choice of indicators depends on the type of reaction. For example, phenolphthalein is used in strong acid, strong base titration because it clearly changes from colorless to a pink at the end point. The titrate is then slowly added from the burette into the flask drop by drop, while gently swirling the flask to mix the solution thoroughly. As the titrate reacts with the analyte, the solution gradually approaches the equivalent point, the point where the moles of titrate and analyte are equal according to the reaction balance equation. The key moment in titration is identifying the endpoint, which is when the color change from the indicator stays permanent. At this point, the reaction is considered complete. The volume of titrate is recorded from the burette. For greater accuracy, the procedure is repeated several times until consistent readings are obtained, usually within 0.1 ml of each other. Finally, the data collected, including the titrate concentration and volume. The analyte volume is used in stoichiometric calculation to determine the unknown concentration using the formula M1V1 equal to M2V2. This entire method ensures a highly accurate and efficient way to find unknown solution concentration.
Now, I'm going to talk about the results. In this experiment, a known concentration of sodium hydroxide were used to titrate a solution of hydrochloric acid to determine its concentration. The titration was repeated 3 times and the following volumes were recorded. As you can see in the table, so the average volume of now used is 25.12 cm3. Using the formula M1V1 equals to M2V2, we get the HCl concentration is 0.1005 mole per dm cube. So the interpretation for this result is the concentration of the hydrochloric acid was determined to be approximately 0.1005 mole per dm cube, demonstrating how volumetric analysis can provide accurate and reliable result in determining unknown solution concentration.
In conclusion, the titration experiment effectively calculated the concentration of an unknown solution by controlling the neutralization of a non-standard solution with the analyte. The endpoint was clearly indicated by measuring volumes properly at the equivalent point with a suitable indicator. The finding indicated that volumetric analysis is an accurate and effective method for quantitative chemical analysis. Experimental mistakes such as parallel error or uneven endpoint identification might degrade accuracy, hence cautious approach is required. Overall, the experiment validated the stoichiometric relationship between the SEM base and highlighted how titration is employed in real-world applications such as quality control, water monitoring, and pharmaceutical formulations.